So the three factors which determine the torque are the magnitude of the force, how far from the rotation axis the force is applied, and what direction the force is acting in. Okay, now all three of these factors are neatly summarized by a simple formula. And so that formula is the following. It's on the next slide. So torque, which is indicated by the symbol tau, is equal to the cross product of R and F. Okay, for now, let's just focus on the magnitude of the torque. So the magnitude of the torque is simply Rf sine theta, and this formula comes straight from chapter 1. You know what the formula for the magnitude of a cross product is, and that's exactly what we're doing here. So let's look at an example. Suppose you have to, let's just stick with the example of a wrench. So suppose I have this wrench, and I'll just draw a nut over here. Okay, and I'm applying a force at the edge of the handle of the nut, so somewhere over of the wrench. So my force is somewhere over here, and I'm indicating the force with this vector arrow. How would I find the torque of the force? Now, first of all, whenever you're measuring the torque, you need to measure it with respect to some reference point. In this chapter, the reference point will always be the axis, on the axis of rotation. So the axis of rotation of this whole system is an imaginary line which is passing through the center of the nut. So I'm just going to call that O. Let's write the O over here. So the axis of rotation is this point about which the system is rotating. Okay, so how do you find the torque of F about this point? So what you do is you first have to draw the R vector, which is a line which starts from the reference point, which is just the axis of rotation, and goes out to the point of application of the force. So please make sure that you fully understand what the R vector is. It's a vector which originates at the axis of rotation and goes out to the point where the force is being applied. Then you calculate the cross product. Once you have the R vector, you can easily find the angle between these two. So let's call this angle theta. And so the torque would just be the magnitude of R, which is just the length of R, multiplied by the magnitude of the force, multiplied by sine of the angle between R and F. Now you might say that shouldn't it be this angle? Absolutely, you can use that angle if you like, but for a cross product it doesn't really matter whether you use the acute angle or the obtuse angle, because sine of theta is the same thing as sine of pi minus theta. So we have this nifty trig identity that sine theta is equal to sine of pi minus theta. So it's just convenient to work with the acute angle when you're calculating a torque. All right, so that is our formula for torque. And here it's very, very important that you understand the meaning of R. So please pause the video and make sure that you understand it if necessary. There's another R coming very soon. So it's very important that you understand what this R stands for. Okay, so R, once again to repeat myself, R is a vector that originates at the reference point about which the torque is being calculated, which, as I said in this chapter, is just the axis of rotation. And it terminates at the point where the force is being applied. Okay. Now, this formula can be written in a slightly different way. So suppose I make this geometry construction, and for that let me just remove this RF sine theta from here. Suppose I do the following. Suppose I draw a line through the force, all right? And then from the reference point, which is the axis of rotation, I make a perpendicular to this line. So I draw this perpendicular so that this is 90 degrees. Okay. Now from geometry, can you tell me what the length of this green line is going to be? The length of this green line would simply be r sine theta, right? So the torque can be written as the torque was Rf sine theta. So the torque is simply r sine theta multiplied by f. It doesn't matter what order I multiply them in. And this particular, so you can see that r sine theta is my green line that I just drew, right? There is a name for this particular length. It's called the lever arm, or r perpendicular. So the torque is also equal to r perpendicular multiplied by f. And what is r perpendicular? R perpendicular is the lever arm. It also has another name. It's also called the moment arm. Okay, let's just quickly review how to find the lever arm or the moment arm. It should be fairly obvious. It's not complicated at all. So let's take another example. So suppose I have this rod which can freely pivot around this point O. And let's say that I'm applying a force maybe in this direction. That is my force, and I'm applying the force over here. My question is identify R and identify R perpendicular, right? So how do we identify R? R would simply be the vector that goes from the reference point out to the point of application of the force. So this is my R vector. And so if I wanted to find the torque using the R vector, I would just do torque equals R times F times sine theta, where this angle is theta, right? Now, if I wanted to find the lever arm, let's do that. So finding the lever arm, it's just a simple geometry construction. The first thing that you do is you draw a line through the force. The next step is to make a perpendicular from the reference point down to that line. So this perpendicular. And this is your lever arm, R perpendicular. Green line is your lever arm. So if you wanted to find the torque using the lever arm, it would just be the force multiplied by the lever arm. Okay. So these are two formulas which give you the magnitude of the torque. And once again, please be absolutely clear about what is R and what is R perpendicular. All right. Okay, now let's talk a little bit about how you calculate the torque in problems. So I have this slide over here. So the first thing that you do when you calculate the torque is you identify the force that's causing the torque. You identify the reference point about which the torque is being calculated. So these are the first two things that you look for. What is the reference point about which I'm calculating the torque? And what is the force whose torque I'm calculating, right? The next step is try to spot the lever arm for that particular force, right? If the lever arm is something that's given, or if it's easy to calculate, then just use the formula torque is equal to lever arm multiplied by force. And that's usually the easiest way to find the torque, as lever arm multiplied by force. Okay, now you might be able to draw the lever arm, but the problem might not immediately give you information about how long that lever arm is, or it might take, you might think that you can find out how long the lever arm is, but you'll have to do some SOHCAHTOA and trig and all that stuff. If the lever arm is not obvious, then it's not worth trying to figure out what the lever arm is. We already have a trig ready formula, which is the formula RF sine theta. So if the lever arm is not is not given or is not immediately obvious, just switch to the other formula, RF sine theta, to find the torque. Okay, so that's the general strategy that you use to calculate torque. Right? Okay, now I'm just going to briefly talk about one more thing here, which is the direction of the torque. Okay, so let's go back to our drawing here. So you might have noticed that the torque is a vector. So torque is R cross F if you write the full vector form. Now from chapter 1, you know how to calculate the direction of a cross product, right? So feel free to pause the video and see if you can figure out the direction of the torque in the diagram on this page. So R points in this diagonal direction, F points to the left. So if you use the right hand rule, you would point the four fingers, you would have your right hand with the four fingers pointing one way and the thumb pointing in the opposite, thumb pointing perpendicular to them. And then you would point the four fingers of your right hand in the direction of R, and then you would curl your fingers in the direction of F, and your thumb would give you the direction of the torque, which in this case would be out of the board, right? So the torque here is out of the board. However, and so that's the direction of the torque vector. In this chapter and also in the next chapter, we are not really going to bother with the actual direction of the torque vector. We are simply going to, it's enough for our purposes to just keep track of whether a certain torque is a counterclockwise torque or a clockwise torque, right? What does that mean? Counterclockwise versus clockwise torque? Okay, just ask yourself, what is the force F trying to do to the object relative to the fixed point O, right? Which way is it trying to rotate the object? Clearly the force F, if it has its way, it's going to rotate this beam in the counterclockwise direction, right? And so we would call this torque, call this torque a counterclockwise torque. CCW, I just mean counterclockwise. It's my shorthand for counterclockwise. Okay, let's say that I have another force which is acting somewhere over here. Suppose I have another force, F1, which is acting over here. Is F1 a clockwise or a counterclockwise? Is it exerting a clockwise or a counterclockwise torque? Let's think about that. I forgot to put the vector arrow here. All right, so my question is this red force arrow F1, is it exerting a clockwise or a counterclockwise torque? The answer is it's exerting a clockwise torque. Why is that? Because if F1 has its way, right, forget about all the other forces. Just think about F1 and just think about the reference point O. So if F1 had its way, then it would rotate the beam clockwise about O, right? And so that tells us that F1 is exerting a clockwise torque. So in doing problems in this chapter and the next chapter, it's enough to just keep track of which torque is clockwise and which torque is counterclockwise. We don't really need the actual direction of the torque vector for the elementary problems in this course. Okay. So that's the direction of the torque. Let's look at an example of applying the torque formulas. So the torque formulas that we just saw were torque equals RF, R cross F, that's the most general formula, R cross F, which can be written as the magnitude of the torque. Remember that if you don't put the vector arrow, it just means magnitude of that vector. Magnitude of the torque is RF sine theta, which can also be written as force multiplied by lever arm times the force, right? So let's look at an example of calculating the torque. I'm going to do one example here, and there's also a nice example on slide 8 of the PowerPoint. I think we'll also work through that one. So so the example that I'm considering is this one. Suppose you have this triangular object which is standing on the ground, and let's say that this distance is 10 meters, and let's say that you're exerting a force of 3 newtons at the top of the triangle, and that force is horizontal, so it's parallel to the ground. What is the torque of this force about the point O? So if the object is fixed at O, right, then when you apply this force at the top, the object is going to topple over about the point O, right? So this force of this 3 Newton force will exert a torque about the point O, right? The axis of rotation is passing through the point O and is perpendicular to the plane of the paper. So the question is, what is the torque of 3 Newton's force about O? Well, how would you answer it? So if you go back to slide 6, which sort of gives you the set of steps that you mentally follow in calculating the torque, identify the force and identify the reference point. So the force is 3 newtons. We can clearly see that. The reference point is O, so we are completely clear about these two. The next step is to try force multiplied by lever arm. So we want to find the lever arm of the 3 Newton force. How do we do that? So finding the lever arm is just a simple geometry construction. We draw a line through the force like this, and then we make a perpendicular from the reference point out to that line. So this is going to be our lever arm, right? This angle is 90 degrees. Okay, so the next thing we want to consider is do we know the length of this lever arm right away? The answer is yes. Clearly it will just be 10 meters. So then we found the lever arm, we already know the force, so we can easily find the torque as torque is equal to lever arm multiplied by force, which is 30 Newton meters. Okay, one brief comment about the unit of torque. You might have, can you tell me what is newtons times meters? Have you seen this combination before? The answer is yes. When we talked about work was force times distance, so that was also newtons times meters, and that particular combination was called a joule. However, joule is a unit for energy, and torque is a completely different quantity. So torque should not be measured in energy units. So even though dimensionally it's equivalent to energy, right, it does not make sense to measure torque in joules. And so that's why when you're talking about a torque, the unit is just Newton meters. You don't call it joules, right? So torque is always just Newton meters, right? So dimensionally it happens to be the same dimensions as energy or work, but it does not make sense to use the same units for energy as torque because they're fundamentally different quantities. All right, so that is how we found the torque in this case. Notice that if you had tried to use the other formula RF sine theta, what would the R have been? The R would just be, the vector which starts at O and goes out to the point of application of the force. So that would have been one of the sides of this isosceles triangle. This would have been your R, right? And then you would have needed to know the angle between R and F, which is this angle. And so if you wanted to use that method, you would have had to do some geometry, some SOHCAHTOA and all that to figure out the angles and the length of R and all of that stuff. And if you do that, you'd get exactly the same answer. But we didn't need to do that because the lever arm was obvious. So in problems where the lever arm is obvious, just go ahead and use force multiplied by lever arm to find the torque.